Black holes are often where data disappears, but researchers may have discovered a way to harness their final moments to reveal knowledge about the origins of the universe. Two University of Chicago astrophysicists have developed a technique for measuring the rate of our universe's expansion in order to learn more about how the universe evolved, what it is comprised of, and where it is going. Their work was recently published in Physical Review Letters. The new method, which the researchers refer to as a spectral siren, is particularly thought to have the potential to shed light on the previously mysterious teenage years of the universe. The Hubble constant, which describes the rate at which the universe is expanding, is a subject of intense scientific discussion. Scientists are eager to discover alternative approaches to measuring this rate because the several methods that are currently available give somewhat varying results. Because it has an impact on our comprehension of major concepts like the age, history, and makeup of the universe. Verifying the accuracy of this number is very crucial. Utilizing specialized detectors that detect the cosmic afterechoes of black hole collisions, the new study provides a method for performing this calculation. On rare occasions, two black holes will collide in a collision so intense that it will literally cause a ripple in space-time that will span the entire universe. These ripples, which are known as gravitational waves, can be detected here on Earth by the Italian observatory Virgo and the American Laser Interferometer Gravitational Wave Observatory, LIGO. Nearly 100 pairs of colliding black holes have been studied by LIGO and Virgo during the last few years. How big the black holes were can be determined from the signal of each encounter. However, while the signal has been traveling over space, the cosmos has expanded, changing the signal's physical characteristics. One of the two authors on the article, Chicago astrophysicist Daniel Holes, said that if a black hole were moved earlier in the universe, the signal would shift, and it would appear to be larger than it actually is. The universe's expansion rate can be determined if scientists can develop a means to gauge how that signal altered. Calibration is the issue. How can they tell how much has changed from the original? Holes and first author Josimora Esquiaga suggest that they can utilize our newly discovered information about the entire population of black holes as a calibrating tool in their new study. For instance, current research indicates that the majority of black holes that have been found have a mass of between 5 and 40 times that of the Sun. So, Esquiaga, a NASA Einstein postdoctoral fellow and Kavli Institute for Cosmological Physics fellow working with holes at Chicago, explained, "We measure the masses of the nearby black holes and understand their features, and then we look further away and see how much those further ones appear to have shifted. And this provides you with a measurement of the universe's expansion." The spectral siren method, which the authors referred to, is a fresh take on the standard siren method that Holes and colleagues have been developing. The name is an allusion to the astronomical standard candle methodology. The technology may one day offer a special view into the teenage years of the universe, roughly 10 billion years ago, which are challenging to study with other techniques, which excites the scientists. This will be possible when LIGO's capabilities increase. Researchers can examine the universe's earliest moments using the cosmic microwave background, and they can examine nearby galaxies to learn more about the universe's more recent history. The in-between era, however, is more challenging to attain and is of particular scientific interest. We are highly interested in researching this crucial transition, where dark energy replaced dark matter as the main factor in the cosmos around that time, said Esquiaga. The authors added that another benefit of this approach is that it reduces uncertainty brought on by gaps in our scientific understanding. The approach may directly identify and correct for faults by employing the complete population of black holes, according to Holes. The alternative techniques for calculating the Hubble constant are based on the physics of stars and galaxies as they are currently understood, which is a very complex area of physics and astrophysics. This implies that if there is something we don't yet know, the measurements could be far off. This new black hole method, however, is nearly entirely based on Einstein's theory of gravity, which has withstood all previous attempts at testing it and has been extensively examined. This calibration will be more precise the more readings they obtain from all black holes. "We need thousands of these signals, preferably," said Holes, "and we should have even more in the next decade or two. At that time, it would be a really potent way to learn about the cosmos."